Okay, Livestream läuft. Dann herzlich willkommen zum Finale vom 12. German Young Physicists Tournament. Herzlich willkommen. Wir haben 3 Teams im Finale. Es wird sehr, sehr spannend. Es war ein knappes Rennen gestern, ein langer, langer Tag. Die 3 Teams sind auf Platz 3 in der Vorrunde, waren aus Bayreuth das Team um Benjamin Graf, Elisa Schöps und Daniel Schulgin. Die sitzen hier schon rechts von mir. Dann auf Platz 2 aus Berlin, hier links von mir, das Team Kurt des Knappen um Simon Hermes, Rushiesai Nutalapati und Kurt Stiller. Und noch 45 Minuten Pause hat das Team aus Lörrach, ganz im Süden aus Baden-Württemberg, die sitzen hier direkt vor mir, Benedikt Baum, Johann Hoffmann und Maxim Rasch. Genau, ich stelle euch noch ganz kurz vor, welche Präsentation wir gleich hören. Jedes Team muss einmal präsentieren und einmal diskutieren. Es sind jeweils Dreierteams, das heißt, ein Schüler oder Schülerin hat Pause zwischendurch oder eigentlich das ganze Finale mehr oder weniger Pause, aber muss natürlich helfen oder darf helfen ganz viel. Also ganz arbeitslos sind die auch nicht, die Dritten. Genau, wir beginnen mit dem drittplatzierten Team, das war hier rechts von mir. Benjamin Graf wird seine Präsentation zu Tripping Faucet halten und Rochil wird dazu diskutieren. Nach 45 Minuten dauert ungefähr ein Match, wird Simon seine Präsentation zu Wirtz Pump halten und Maxim wird dazu diskutieren. Und in der letzten Runde, nochmal 45 Minuten später, hören wir einen Vortrag zu Magnetic Assist von Benedikt und Elisa wird diskutieren. Genau, dann haben wir hier eine wunderbare Jury vor uns. Die würde ich noch ganz kurz vorstellen und dann geht's richtig los. Genau, ich fange hier rechts einmal an. Das ist der Felix Rüdiger aus Wuppertal, Ottmar Winkler aus Meißen, Maxim Walter aus Hamburg, Hakim Rachidi, er steht hier, glaube ich, als Holzminden, inzwischen in Göttingen, glaube ich, aber er war Holzminden am GYPT-Standort. Dann Jonas Kalferam aus Kassel, Rebecca Zirkel aus, jetzt muss ich gucken, Bochum, Thomas Grillenbeck aus Dachau bei München, Cosma Standel, schlecht. Wo ist er? Aus Erlangen, Entschuldigung. Endre Kayari aus Hameln und Felix Greier nochmal aus Kassel. Und dann möchte ich noch meine wunderbare Chairwoman für dieses Finale vorstellen. Das ist Carina Karnitz. Sie wird ja durch das Finale moderieren. Aus Ulm. Genau. Damit begebe ich an dich.
Super, vielen Dank für die Einführung. I think now it's also the time to switch in English as the official part is starting of this physics fight. The teams are already introduced, the jury is introduced, so I would say we can go straight ahead and skip to the preparation time. As always, you can just get started once you feel ready. We have Sebastian at the clock that will just start your presentation time once you're ready. Have fun.
Perfekt. Ja, super. Okay. Yeah, I think it's working. So I think I'm ready and we can start. Hello, I'm Benjamin Graf from the team Under Pressure. And today I'm going to present you my results on problem number 6, dripping faucet. The task says, A leaky faucet develops interesting dripping patterns where the time between drops depends on the water flow rate. Investigate this phenomenon and study how it depends on relevant parameters. Here you see a video displaying the phenomenon. As all videos in my presentation, it is a slow motion, reduced to 1/6 of the playback speed. In my talk, I will at first show you my experimental setup. Then we will handle the pending drop before introducing two different types of falling drops. The main drop that we will call leader and its directly following so-called satellites. In the end, complete dripping events will be analyzed. But let's begin with the experimental setup. A simple water faucet suffices as first experimental setup. I use background illumination when filming the droplets. Of course, we can also add a scale to measure the flow rate. For experimental parameter studies, I've also built an advanced setup. Using a ball valve, I'm able to measure with constant flow rate over a longer period of time. The flow rate only changes about 1% in 10 minutes, sometimes even less. But I can also vary the filling height and thus the flow rate with a second water container. With this setup, I'm able to vary the nozzle diameter. Now that we know how to create the droplets, let's start investigating them. We begin with the pending drop, which hangs at the faucet. For small enough flow rates, which are proposed by the term leaky in the task, the kinetic energy which determines the shape of the pending drop mainly stems from gravity. Therefore, this shape only depends on the current volume of the drop, not the flow rate. We can see that in the two videos here. Despite having different flow rate, they end up showing the very same shape. But now let's have a closer look at this function mapping the drop volume to its shape. In the beginning, due to the slow refilling of the drop, it is quasi-static and can easily be predicted. In the quasi-static case, there are only two forces acting on the drop. Gravity is pulling the drop down, while surface tension holds it together. As soon as the force of gravity exceeds the force of surface tension, the drop cannot be held back anymore and falls. We call this maximum volume of a stable pending drop critical volume. We can estimate these two forces and thus the critical volume, but for a more accurate determination, we need to compute the whole shape of the drop. And differential equations can be derived using the principle of energy minimization. I've solved the shape of the drop matches very well. Using the simulation, we can see which shapes are stable. They are marked with a continuous line here. But the simulation also yields unstable solutions that would not occur in reality. The maximum volume possible is therefore our critical volume. Comparing the rough estimate to the more accurate simulation and the measurements, we can see that they are matching quite well. So after this volume is reached, a drop starts to fall. But not only one drop. Directly after a so-called leader drop, there can follow multiple so-called satellites, very small drops that are formed due to the following reason. The satellites stem from the neck of the leader, where its detachment produces tiny perturbations of all wavelengths. Particular wavelengths grow until the neck breaks and the satellites are formed. This process is known as Rayleigh plateau instability. As we've handled the critical volume, it would be quite interesting to also know the volume of the satellites. I can show you my measurements here. I enumerate the satellites starting with 1 for the first satellite after the leader. In this plot, volume ratio is shown as a function of time difference to the main drop. Even though the satellites are caused by instabilities, their volumes are quite reproducible. Their typical volume decreases with increasing satellite number. But now let's go on to the most obvious drops, the leader drops. Here I plot the volume of satellites and leaders for different flow rates. We see large and small drops for every flow rate, but the size of each type is nearly independent of the flow rate. When looking at this photo, we see that the leader is the by far largest drop, that is followed by the already investigated satellites. Their volumes are separated by approximately 1 order of magnitude. So now let's have a look at the temporal patterns. We start with the time between drops. It must decrease when the flow rate is increasing, as the drop volume is nearly constant, as we've seen on the last slide. In the lower part of the plot, I show the distribution function of the dripping time intervals for multiple flow rates. On the top, the density is plotted. The distribution is bimodal. As displayed by the colored bumps, the typical time difference from the preceding drop decreases with increasing flow rate. However, we see that this is not the case for the satellites that follow very shortly after the leader drop. As all three flow rates show nearly identical behavior here, the mechanism of satellite formation must be independent of the flow rate. To sum up, the behavior at low flow rates is quite predictable and in parts also independent of the flow rate. To find another type of interesting patterns, we need to increase the flow rate and dripping frequency a bit more. In order to measure many drops, a video analysis is needed that tracks the individual drops. I do this as follows. After separating the foreground using a binary threshold, I find the contours using OpenCV. The drops are sliced in disks of 1 pixel height. I assume that each disk is circular. Then I can easily calculate the volume and the center of mass of each drop. To switch between the units in the video and reality, I use a feature of the Faucet as a calibrating length. For taking times with subframe accuracy, I interpolate the trajectory of every drop. The advantages of this video analysis become evident when looking at the numbers. Using it, I was able to measure more than 1/3 of a million individual droplets. With a sample rate of approximately 1 frame per 8 milliseconds, I reached a standard deviation of the intervals of about 0.2 milliseconds, including noise due to experimental imperfections. This scale of accuracy is absolutely crucial when trying to resolve the quasi-periodic and chaotic patterns of the system. These patterns are most clearly displayed by a plot type called return map. Here, each point corresponds to one drop. On the horizontal axis, the time difference to the preceding drop is shown. And on the vertical axis, we see the time difference to the following drop. The time before a leader drop is large, so we start here at the filled green circle. We can read that the time to the next drop is small, so we end up at the empty circle. For the next step, we start there. Now we've got two possibilities. The next drop could take quite some time, as shown by the dashed lines, and we would end up with a new leader drop before. But for the picture shown on the side, after the first satellite, another satellite follows, and we can read that it follows even closer. So now that we've understood this type of plot, let's use it to take a look at the pattern of leader drops only. In this plot, only leader drops are shown. That is, we consider only complete dripping events as a single point in this graph. Whenever the points lie exactly on the diagonal, we've got a simple periodic pattern. The time to the preceding dripping event equals the time to the next dripping event. When the points do not lie on the diagonal, there must be an interesting dripping pattern, as now the time changes between events. How can this be, given the pending drops were so predictable? When a leader drop and its satellites are emitted, some water remains at the faucet. This residual pending drop oscillates. The next dripping event is then critically affected by the exact phase of this oscillation. This means there are two typical timescales: the time before the leader drop, Tn, and the period time of the pending drop's oscillation. For finding the latter, we plot the height of the pending drop between two dripping events. The oscillation can clearly be seen. The period time of this oscillation increases slightly as the residual drop grows again. But ignoring such subtleties for now, the oscillation of the pending drop dictates a time unit for the dripping event time differences. The results can be seen in the return map where we have started, now flattened such that the diagonal becomes the y=0 line. The simple periodic regions at 0 appear to be spaced at equal time differences. As we can clearly see here, these differences are very close to the oscillation period of the residual drop. So now that we've understood the reason, let's have a closer look at the interesting patterns and zoom in. We can see that the lines in the return map seem to split and form a kind of bubble. This process is known as period doubling. After a big drop, there's a shorter interval and a smaller drop follows. Then we jump back to the first branch where we have started. When we increase the flow rate more and more, the lines get less and less sharp. Let's again zoom in on a certain area. This return map doesn't even have significantly many points on the diagonal. Multiple dimensions seem to evolve, while some kind of structure is still preserved. Especially in a strip at around 0.3 seconds, it can be seen that a specific interval can have many different following intervals. This is a strong indication for chaotic behavior in this region. Speaking of chaos, let's come to the last return map of this talk. Here I plot all drops, as there's no clear scale separation between leading drops and satellites anymore, neither in volume nor in time difference. There's a gradual transition from red to blue, and the regions of the red and the blue drops touch each other in the return map. So let's increase the flow rate even more. For very large flow rates, we see a well-known picture: calm stream of water eventually breaking into drops far below the faucet. However, this state is not necessarily stable yet. If I disturb the stream, we eventually go back to dripping without changing the flow rate. So a last question remains. What happens if we decrease the flow rate again a bit? The calm stream can expand and retract itself up to the point that pure dripping is re-established. For a single flow rate, different behaviors are metastable, either fast dripping or flow. Which behavior we see depends whether we come from lower or higher flow rates. We see a hysteresis. Within the hysteresis, spontaneous transitions happen. When the system gets disturbed, it can of course transition as well. So let's conclude. I've shown that the pending drop's shape and the critical volume can be well predicted. Following the leader drops, we have investigated the satellites and their falling pattern. We have also seen that the volume of a falling drop is independent of the flow rate, therefore the time between drops scales with the flow rate. Furthermore, I've shown that simple periodic and interesting patterns alternate when varying the flow rate. The interesting patterns in this case are quasi-periodic patterns. The difference in time difference between these simple periodic patterns equals the oscillation period of the remaining pending drop. Finally, I have presented return maps, revealing the interesting structure behind fast dripping. And above that, spontaneous transitions into continuous flow happen. Thank you for your attention.
Thank you for the nice presentation. Now we have 2 minutes preparation time for the opposing team, and the jury can start marking the presentation. To the audience,
the time interval for the droplet to actually form to be very slow, much less time. So the rate at which the droplet drops and the amount of drops that drop will be much higher, right?
I agree with you.
And from this, would you say that the droplet would be more symmetrical in shape or not?
Are you speaking about the falling drop?
Yeah, about the first leader drop.
I think that the first leader drop is critically affected by air drag, and I think that this is like if the surface tension goes less and decreases, I think that the shape becomes less and less symmetric. But I think that the shape of a falling drop is not so interesting as the shape of the pending drop.
Okay, I think we both agree on certain parameter variation. I mean, temperature would be a very nice parameter to vary because obviously you can look at further relevant parameters that connect temperature with surface tension, and that might be a possible improvement for later, but we can move on. have you any sort of analysis in your presentation or appendix regarding the Weber number or how that would actually affect your system? Because I'd assume that with the lower Weber number, surface tension dominates, right? And from that, one would try to classify different not regimes, but different processes in the phenomenon where one would expect a droplet to be more symmetrical, or the rate at which the droplet drops to be much faster or slower. Do you have any qualitative or any calculation of the Weber number for different measurements that you've done? And if so, how do the trends look?
No, I don't have calculations of the Weyl number, as I think that...
I said the Weber number.
Oh, I'm sorry, I didn't understood you acoustically. No, I don't have such calculations.
So if you have a high Weber number, what would you actually expect?
I'm sorry, I don't know what this is.
Well, I believe that with the low Weber number surfaces, you say was chaos. But do you have any actual proper verification of the chaos in the system? For example, have you calculated the Lyapunov exponent, or do you have a basin of attraction where you find a strange attractor, or how exactly did you come to the conclusion that you have chaos?
Well, I did not calculate the Lyapunov exponent, as I don't have a simulation for the chaotic patterns.
Okay.
I only have a simulation for stable pending drops,
okay,
or quasi-static pending drops. I think that this might, well, we have different indications for chaos. Here we have this specific interval that can have many different following intervals. We can also see, this is, in my opinion, hinting at a strange attractor, and also this return map is
But you do not have any calculation of the Lyapunov number, so you cannot completely be certain that chaos is there. Well, it is well known that there's chaos in the system, but you don't have any quantitative proof that there is chaos in the system, right?
No, I don't, because it's very difficult to read the complete state space out of the single return map.
Okay, and so if you had a Lyapunov number, at what number would you consider chaos to be there? Can you define what range where you would have the Lyapunov the exponent? At what number range would you call that chaos, and where would you not call that chaos?
Well, a positive Lyapunov exponent, so it's chaos.
Perfect. That's that. But moving on, I'd like to talk about the hysteresis. If I understand correctly, if you have a certain flow rate, say period 2, so you have an identical droplet every second drop, essentially, then and you decrease the flow rate back to 1, decrease the flow rate, then essentially you would have some sort of hysteresis where it still follows the period 2 for a certain amount of time, and then it moves back to period 1. Is this what you were trying to convey, or did I miss something?
No, I think that I'm speaking about a hysteresis between flow and dripping.
Okay.
And that flow is, these are the two metastable states here.
And so let's say you have flow rate, but before comes to that, I actually didn't see too much regarding different periodicities in your presentation. Could you briefly talk about what are all the different periodicities one can experimentally investigate? Because I don't know that you talked about the periodicity in the sense that you explained what exactly happens. You have some general rule of such, for example, periodicity 1, there's a constant identical droplet falling every time. What are the different periodicities that you have experimentally observed?
Well, we can see that here in this return map where we say one drop is
very shortly, just here, what periodicities exactly?
We have period 2, and I think that we also, so period doubling, I think that we can also observe period quadrupling, but I don't have quantitative
Would you also believe that after you slowly enter into the chaotic region, at certain points you would actually have some stable patterns? So maybe you could hit, for example, period 3, which sometimes happens because it is kind of a stable region, stable periodicity in the chaotic region, right? Did you investigate this? If you haven't, what would you expect? Would this be possible to see in experimental setup or no?
Well, I think that this would require very, very low noise to see this, but I think that theoretically it would be visible that you have stable regions in the chaotic.
So you believe that there might be a possibility you can see that experimentally. It is just you did not observe this pattern.
Yeah, I think that at chaotic regions, noise becomes more and more important, and I cannot eliminate this noise completely.
If we remove the odd periodicities, which only occur during the chaos region, right? Even periodicities like your period 2, then your period 4, would you expect this to increase? Would there be a possibility you see period 8? Or how exactly does this? Because theoretically, one can expect this to go on to infinity of such. And this essentially is because what essentially determines this is you have this droplet, right?
Yes.
And there is a certain time range, let's call that a T1, for example. That's how long it takes for the droplet to form here and then drop, right, essentially. And when it drops, there's a certain amount of liquid that stays here and that oscillates. And we can call that rate T2. And the reason why you see a very stable period 1 is because T1 is far, far greater than T2, right?
Yes.
And as you essentially increase the flow rate, what would happen is that because of the increasing flow rate, T1 would actually come closer to T2, right?
Yeah.
And what exact periodicity would you expect there to be proper, and then at what point would there be chaos?
Can I shortly interrupt you? Let's call this Tn and T oscillate,
okay.
Because, this is how I called it in the presentation, but, okay. And so I think that if Tn becomes in the region where the oscillation didn't settle down, so it becomes in the maybe 1 order of magnitude greater than T oscillate, where we have 10 oscillations, then we come to these period 2 things, and then
so there might be an upper bound on how many periodicities you see, and then the chaos, right? So one would not say that you have some period 16 or such, anything like that.
Yeah.
Okay, but you do not know the upper bound of the periodicity because that was not something you experimented with.
Yeah, I have too much noise for that.
Okay, perfect. And lastly, for the satellite droplets, you said, obviously there are many parameters that would actually affect it because this is essentially the Rayleigh plateau instability, as you said. But what would be the most important parameter? Would it be surface tension or inertia?
I think that it would be surface tension because the properties of the...
And if you have a higher inertia, would you expect more satellites or less?
I think that, with increasing flow rate, there will be more satellites.
Okay, perfect. So I want to conclude the discussion. First of all, we talked about the basic explanation, which was not so well presented in the presentation because there were competing factors, which I actually prefer because we got a deep dive into the other stuff, but we discussed the basic explanation. Then we had a qualitative insight into some geometric parameters, such as surface tension, also the temperature, and then we talked about the Weber number, which could be used to further classify, and some aspects of the chaos, some hysteresis, and the specific periodicities, and forming of stable droplet patterns. I think I thank you for the discussion. Thank you.
Thank you too.
Not so great, so.
Okay, thank you very much. Now it's time for the jury questions. Can you please raise your hand? Yes, Felix, you have an urgent one.
Yes, to the reporter. Can you make any, you observed a stable periodic regime, can you make any prediction for the period of the drops in this regime dependent on relevant parameters?
Well, of course we can investigate this period depending on the flow rate, which I've done here, and then depending on surface tension, as we've already said in the discussion, this period time would decrease when surface tension decreases.
This is an experiment. This is experimental data, correct?
Yeah.
Do you have a theory which can predict this?
Where we can go back to this critical volume. As soon as the critical volume is reached, a drop starts to fall, and then we can say
Okay, thank you.
Cosmas, please.
You showed us a second experimental setup with different nozzle sizes. Did you use it for this experiment? Because the videos, I think the videos all were from your first setup, right?
Yeah, mostly. This video here is from the second setup, all the return maps I've shown is from the second setup, and where we have these critical volume theory experiment comparison, where I used the second setup, and then I also varied the nozzle diameter, and I've seen that for very small diameters, I've got very periodic regions, and for very large radii, I have like very interesting patterns.
Okay, thank you.
More questions? Hakim, yes?
To the reporter, you showed us the Poincaré map for Tn to Tn plus 1.
Yes.
Have you any plot for Tn to Tn plus 2?
No, I don't have. I'm sorry.
Okay.
To the opponent, if you scale up everything in this setup, except for the molecules and so on, what would you expect? What would change here?
I mean, obviously, the respective forces are not going to scale linearly. Of course, you have surface tension, effects of surface tension, but also capillary forces, but also the adhesion to the nozzle, because it also depends on the nozzle material. If you have a hydrophobic versus hydrophilic surface, for example, if you use polythene, then it differs. But if you scale it up after a certain range, I would not expect there to be a significant droplet forming, just due to the physical constraints of the setup.
Who else wants to ask a question? Yes, Cosmos again.
Maybe to both of you. First, the reporter. A normal faucet has a mesh-like structure underneath. How do you think that influences the dropping pattern? And after you can answer too.
Well, this only influences the water stream, and as we are at very low flow rates, I think that this wouldn't be so important. Maybe at the chaotic regions where the flow rate is like not negligible, it will become a bit important, but as the flow rate is very low, I think that this doesn't have any great effect.
I agree with the reporter, but also sometimes it might not be as easy to model the droplet shape. If, for example, young Laplace would not be so easy.
Fine, because we have another quick question.
A follow-up question to my former question. You have some maps on this slide which are symmetric with regards to the diagonal. Can you maybe physically explain this?
Well, that says that we are really in the period 2 region here. So we like a drop falls here, and then the next drop here, the next drop here. So we are like switching.
Thank you. We have to stop here because also the jury questions have to stay in time. So now the jurors have to do a very different calculation of summing up. I think it's 8 different numbers. Don't forget your 1. 10 seconds. Okay, I think we have it. We have one speciality in the finals compared to the fights we had yesterday, because today the marks will be held up. So you see immediately how the jurors think the fight went. And so please prepare your mark for the presentation. Not quite yet. Is everyone prepared? Everyone has found the little booklet? Yes, okay. Now you can hold it up. And for the report, we have an 8, 7, 8, 8, 7, 7, 8, 8, 9, and 9. Thank you very much. Big round of applause. And for the discussion. And now hold it up. We have 8, 7, 8, 8, 8, 8, 8, 8, 9, and 9. Very good. Bochum. Yeah. Rebecca. Yeah. Okay. Now I would like to have some comments from the rather high or rather low marks. So I think, for instance, Rebecca, could you comment on your 7? What were maybe the points you were missing? What did you like?
Yeah, I think the temperature variation would be very interesting, and it was one of the biggest issues that I only thought of in the discussion, and I think that would be very interesting. So that's 7.
Yeah, thank you very much. And now maybe Felix, can you comment on your 9?
For me, the presentation was pretty good, and you had awesome graphs. So the visualization in general was very awesome, and yeah, it was nice to hear you talk about your project, and you did it very well, especially for the experimental setup.
Thank you. Does anyone else have a pressing remark to this very impressive report? Okay, then we can go on with the discussion. There it was rather uniform. We had 1 7 with Ottmar over there.
Thank you. Let me explain it a little bit. You showed us a deep understanding of the problem and how you would like to talk about chaotic behavior and how to handle it. But on the other hand, you did a little bit our job to prove that both of you had understood the problem and the physics behind. But the task, in my opinion, at the physics fight is to develop the problem to a higher level. And if you look for the task, it's about dripping patterns and not about chaos. You spend a lot of time talking about chaos. I'd rather had more information, more developing the problem in the direction of patterns.
Okay, thank you very much. And now, Endre, can you comment on your 9?
Sure. In my opinion, you brought up very interesting and also great points that would improve even more the project. You showed us deep insight, and hydrodynamical problems are always very difficult on the theoretical part as well as on the experimental. And so here I grade always a little bit higher.
Thank you very much. Let's have another big round of applause for the 2 teams and also for our jury. And I think now we have a miniature break for reshuffling the teams, for returning your keys, for returning And we will have Simon Hermes presenting us the Wirtz pump. And we have Maxime Rasch from Lörrach, who is going to hold us the discussion. So, I think we are ready for the next fight, are we, Sebastian? Okay, so your preparation time has started. Just start whenever you are done.
Funktioniert das? Okay, sehr gut. I think I can start. All right, so hello, my name is Simon Hermes. I'm from the team Kotis Knappen, and today I'm going to present to you my solutions for this year's 16th GYPT project, the Wirtz pump. All my research was done in cooperation with Onora Miss and Sophia Saunders. Let's begin with a quick overview. First, I'm going to do some preliminaries and a basic explanation. Then I'm going to show you my experimental setup, and then I'm going to show you my theory and data, and then I'm going to talk about our task fulfillment. Let's start with the preliminaries. We're going to look into the movement of the water plugs inside of a pump, first of all, and we're going to consider a 360-degree turn. At the start, you can see that water plug W1 is being scooped up when turning 360 degrees and put in right there. While all the other water plugs are moved one loop upwards, and which means that the water plug W4 is being pumped out of the pump, and basically the state of all the plugs remain the same afterwards. Now let's look at how pressure is generated inside the pump. When there's a water column being pumped upwards, there's pressure put on the exit of the pump right there, which displaces the water plugs, which then create the pressure through gravitation that counteract this pressure by the water column on the top. And this pressure is the pressure we're going to be looking into in this presentation. Now let's start with some system parameters. First of all, some non-geometric parameters. We have the submersion depth, and we have the angular velocity of the pump. And some geometric parameters, we have the diameter of the pipe, the radius, the average radius of the pump, the maximum radius of the pump, and the difference between the radii. In the future, if I'm referring to the diameter of the pump, or any diameter, I'm referring to the diameter of the actual pipe, and if I'm referring to radius, I'm referring to the radius of the actual pump. Now let's get to experimental setup. First of all, we had a glass base plate with markers to ensure that our measurements are reproducible, and different roll-up spirals made of PVC to change some parameters in the system. To measure the height, we put a motor on here that turned the gas base plate, and we put another pipe which just pumped everything upwards. But while we were turning the pump, we needed to also turn the pipe that was pumping upwards, which was very inconvenient. So now to a solution for that, we just measured the pressure. We just stuck a pressure sensor in front of a pipe pump and measured the pressure. Now let's get to our actual evaluation of our measurements. This is a picture of raw data, a plot of raw data we got, and we just wrote the Python script, which basically just takes peaks, where peaks need to be at least 5 seconds apart and need to be the highest value in a 5-second window. Now let's start with our theory and data, beginning with our assumptions. First of all, we assume that Pascal's law is applicable, meaning the difference in pressure is proportional to the difference in height. We also assume the ideal gas equation to hold true, and there to be an ideal gas. You can see the equation right there if you want to. We also assume the radius of the pipe to be constant to these calculations. We assume that air or angular velocity can be ignored, and we assume that the water plugs block air from moving between chambers, which means there's no significant bubbling between different air chambers. All these assumptions are justifiable, and we have physical basis for them. First of all, the physical basis for assumption of ignoring the angular velocity. We just use this device right here to turn our pump, and we measured the pressure, and you can see you can very easily plot a constant fit through our different angular velocities, so I think we can assume this assumption to be applicable. Then we looked at the assumption of water pockets being stable. We used the pump of diameter 1.5 centimeters, and you can see there's a lot of bubbling inside, which is why we only use, which is like more or less the boundary of where you can actually assume that. So we always used a pump with a diameter of 8 millimeters or lower to ensure that there was no bubbling. Now let's begin with our actual theoretical approach. First of all, we defined a few angles. Delta phi is the angle subtended by the water plug. Phi I is the angle from the resting position of the water plug to the displaced position of the water plug, and phi A plus and phi A minus are the upper end of the water plug and the lower end of the water plug respectively. From these, you can calculate these two lengths right here with some basic trigonometry, phi A plus and phi A minus. And this you can plug into Pascal's law. I already told you about Pascal's law. We can then make some easy rearrangements using some trigonometric identities. Now we'll define a constant called kappa, which is defined in this way, where all the values in there are assumed to be constant for our system. And we're also adding some pressure that is lost because of friction inside of a pump because the system is very turbulent. Now let's make some geometrical observations on a system. We want to define the angle phi I just using the angle phi I minus. We're doing that by first looking at the angle phi I minus and then taking half delta phi, then this angle theta, which is just the angle subtended by the air, and another half delta phi, and just then going back 2 pi to ensure that all the angles are inside of 0 and 2 pi. Then we plug in for theta the formula right here, which we can calculate by just the volume of a torus. This we can rearrange using the ideal gas equation to get this right here, which we define as a new constant called tau. In there also everything is assumed to be constant in our system, and notice that there's no diameter, meaning in neither of the equations, meaning we can the diameter shouldn't play a real part in the generated pressure. So this is our final equation right here. Now putting everything together, we get this system of equations here with 2i minus 1 equations and 2i unknowns. So we can't solve the system you can't close the system of equations, so we need to think of something. What we're going to be doing is looking at the innermost angle inside of a system, like the angle that would be right here, this one. In most of our measurements, it was the fourth angle, so we call it phi 4. And we know that at the point where the pump stops working, there's going to be overspill. So the air plugs are going to be displaced to a point where they just spill over into the next loop. So we know that the angle phi 4 is going to be between 0 and pi. So what we now can do is just iterate from 0 to pi of phi 4 and just use the maximum pressure. You can see that right here where we iterated through phi and just used the value with the highest generated pressure. We're also always solving a system of equations using the Newton-Raphson method. Now let's look at some experimental verification of our theory. Right here we measured the submersion depth with the amount of loops 4 and radius of 16.5 centimeters. As you can see, the blue line right here is our theoretical expectations, which we calculated, and the red measurement points are what we actually measured. And you can see that our measurements agree with our theory quite well. Now we also verified the radius, where we used only 3 loops to not use as much pipe, and we submerged the pump 5.7 centimeters. For that, we then again plotted our theory and got this graph right here. And as you can see, again, the measurements agree quite well with our theory. Now let's talk again about the task. The task stated that we need to calculate the pumping height. So far, we only calculated the pressure. So calculating the pumping height, we can do by using Pascal's law again. Basically just doing some basic rearrangement and getting this formula right here. We also obviously wanted to prove, or at least check if that holds true. So for that, we used a setup I already described to measure pumping height. And for the same set of parameters, also measured the pressure generated using our pressure sensor. And from the pumping height, we calculated the expected, the pressure acted upon the pump by the water column using the formula I just derived. And as you can see, the measurements agree quite well with each other. So I think we can use this theory. Now let's look a bit at points where the pump stops working. And we're looking at the maximum frequency we can use. So while the water flows inside of the pump, there is a pressure that creates a pressure loss. I mean, there's friction that creates pressure loss. And through this friction, the water plugs are displaced more and more. And the difference in pressure between the pressure this water plug creates and this water plug creates, if this difference is greater than the pressure created by friction, the water plugs can still move more or less freely inside of our pump. But if the pressure created by friction is greater than the delta pressure, the pump stops working because the water plugs basically just move with the pump, and that just stops the pump from working. Now we want to calculate this friction, the pressure created by friction, using Darcy-Weisbach equation. We can rearrange this equation for the frequency and calculate the Darcy friction factor using the Kohlberg-White equation. And then we also can calculate from that expected trends. First of all, we can vary submersion depth and see that we expect the maximum frequency to be at about 300 RPM. And we can measure the radius and can see the expected frequency between be at 450 and 300 RPM. And we can see for increasing radius, the maximum frequency decreases because the outermost water plugs are moving quicker because the radius is greater. We also verified that experimentally. We just used the device I already showed you to turn the pump, and we found that the maximum frequency we can use is about 300 RPM, and you can see here the water plugs moving upwards. Now let's get to our overview. We derived, we found some, first we proved our assumptions, then we derived a theoretical model and found some limits of our theoretical model. Now let's look at task fulfillment. So first of all, we recreated the phenomenon. We found a basic explanation, and we created a sophisticated experimental setup to measure all the relevant physical quantities. We also created an extensive theoretical model, which we had to solve numerically. And we compared the theory and our experiments and some experiments where we verified the most relevant parameters, and we found very good agreements. Thank you very much for listening.
Thank you. Now 2 minutes preparation time.
So, I can say. So, first of all, thank you, Simon, very much for this nice and insightful presentation. Unfortunately, I missed a lot of parameter variation as well as sufficiently huge gaps in theoretical as well as experimental comparison. Therefore, I would like to start with one missing parameter I've missed in this investigation, starting with the basic explanation of the rotation speed. Unfortunately, this came quite a bit short on what effect the rotation speed have, especially for really high values and especially very low values. If we could move to a basic explanation. How does an increasingly high velocity affect, angular velocity affect this phenomenon?
So higher angular velocity basically just means that the water plugs need to move faster through the pipe, which means more friction, and so the pressure generated will be smaller, basically, if you understand what I mean.
Okay, so that means, but at some point, if the angular velocity would be very high, we also have additional inertial effect in this pipe system, where this is not only for water once per revolution to get water filled in, right?
I don't really think that the inertial effects play any significant role in the system.
Okay, thank you. Especially for the low velocities, I would agree with you, but let's stay for the angular velocity. In your experimental setup, you showed us a graph where you say that over the angular velocity, pressure stays approximately constant up for a rotation speed of 3 seconds.
Yeah, 1 second.
My question is, so have you double-checked your measurement of the rotational speed? Because what is essentially happening here that the motor with which you're powering this pump must compensate for the additional power, because at the end of the pipe system, if the hydrostatic pressure would increase even further, for every once revolution, we get a higher filling height, therefore a higher hydrostatic pressure, right? Therefore, the power of the motor must compensate for that additional weight.
There wasn't any water column on top, we just had the pressure sensor.
Oh, okay, so therefore you're, okay.
Yeah.
Thank you very much. Then this is actually quite sufficiently cleared up. If we move on to your theoretical considerations.
Yeah. Which was exactly?
Exactly, we can start here. You're assuming essentially that if we look at this cross-section of the pipe system, that we always fill up this pipe up until a certain value, so we never have, for example, a slowly filled gap in between. Could this happen for especially very low velocities? That is not completely filled up, this height here?
With water, you mean?
Yes.
Because of surface tension, I don't think so.
You think surface tension plays a significant role? So this is due to surface tension that is completely filled up.
I mean, the surface tension makes it so that the plugs are, I think, perpendicular. What was it? Senkrecht, oder? Senkrecht, der englische Begriff.
Vertical.
Vertical, exactly. Vertical to the pipe, and we actually saw that there was, even if you just keep it still, there isn't like any such effect occurring.
Okay, but so I wouldn't say that this is a surface tension effect. I would say this is just a pressure compression effect. So I believe we disagree on this point. But in your task demonstration, you showed us, if we stay at this topic, that there are air bubbles forming and going from one airlock to another airlock, right? And you said at a certain value of radii, these air bubbles don't occur anymore.
No, I said that if the diameter is too large, there's a significant amount of air bubbling, which basically equalizes the pressures to a certain degree.
In your experimental data, you varied the diameter of the
No, we didn't. We varied the radius of the pump, and I said the radius of the pump, the diameter is always the diameter of the pipe.
So why is it important that that these air bubbles aren't forming?
Because if the air bubbles are forming and bubbling through, the pressure is equalized, and it just makes all the theoretical predictions a lot harder. So, I mean, if there's a very significant amount of air bubbling through, the pressure is just equalized, and we don't create as much pressure, if you know what I mean.
Yes, I agree with you on that point. I have one major problem with your theoretical approximations, because if we move on to the theory where you're introducing a so-called pressure friction.
Yeah.
How is this defined? How do you calculate that pressure friction?
This is just empirical measurement.
It's empirical measurement. Yeah. So you're essentially fitting your theory to your experimental data, is that right?
Yeah, to a certain degree, yeah.
Because at slide 22 you said only with theoretical expectations and not a theoretical modeling. This is due to the fact that you're fitting the pressure friction, right?
Yeah.
Okay. If we move on to slide 27, you show the Darcy-Weisbach equation.
Yeah.
If you could please state to me why do you believe this is applicable for such a phenomenon?
Because the Darcy-Weisbach equation is applicable for, it's just applicable for like tubes with friction inside of tubes. If you know what I mean.
Yes and no. What needs to be happened for that Darcy-Weisbach equation that we have a stabilized velocity profile?
Yeah, we are.
Of course, we're assuming now that we have turbulent flow in the system.
Yeah.
But the question I would ask, the relative velocity of this, so at first, it's important that the system is completely filled up so that we have two non-slip conditions on the inner and outer edge, right? Additionally, the velocity needs, the water needs to move with a steady velocity of some certain point so that we actually have a turbulent velocity built out like something like this. I'm not sure if this is the case. Did you ever, like, for example, calculate the Reynolds number, or do you believe that we actually have a built-out velocity profile, which I highly doubt due to the irregular motion of the water?
The Reynolds number is, first of all, calculated in the Kullback-White equation.
Yeah, but I mean, you need to calculate the Reynolds number in order to show that it's actually turbulent flow.
Yeah, it is. It's turbulent flow.
Okay, I'm going to believe you then.
Yeah, I mean, it's, yeah.
But I strongly disagree with you that the Darcy-Weisbach equation gives us an applicable case for this friction right here, because, as I said, we need a steady stream of water velocity, and I believe that it is not given here due to the rotational motion, as well as the additional turbulences due to the rotational motion are not included in the Darcy-Weisbach equation, right?
Yeah, but I think the rotational motion, how would you use it? What do you use instead?
So, first of all, I believe in general this is quite hard to model, therefore an empirical model just to fit measurement is quite sufficient in this case. But we need to at some point differentiate between what is the pressure loss due to rotational motion and what is due to the steady streamline. And I don't think that this is the main frictional effects we have right here. So, unfortunately, in your, I think we can close up on that point. We agree to disagree. I believe, of course, that this has been much more investigated what this effect the rotational movement has. One parameter, which unfortunately I kind of miss in this presentation, is actually the impact of the angular velocity. Right? Did you investigate the pumping height independent of the angular velocity?
Yeah, I just showed you.
Yeah, please. So.
I measured the pressure, not the actual pumping height, because as I said already, it's very, very hard to actually measure the pumping height. But
okay.
I mean, that's the angular velocity, so.
So over all angular velocities, this stays constant. There's not an upper value at some point for one for one angular velocity where this is not going to. Because initially,
you mean is like a limit angular velocity where the pump stops working?
I can think of that. Yes.
Yeah, I mean, I also.
Because at some point you would just naturally assume that the weight.
I showed you the maximum frequency you can use, and from frequency I think you can quite easily calculate the angular velocity. I'm not mistaken.
Yes, that's right, but you didn't double check anything with your experimental data. Right?
We checked and found that to be 300 RPM, and the expected frequency was 200
Yeah,
RPM.
but I believe we can both agree on the point that one comparison between experimental and theoretical data gives us not a scientific answer if a model actually fits with each other, right?
Yeah, you can say that.
Therefore, I would just suggest you further investigate onto this point.
Yeah, that is a very good suggestion.
Okay. Okay. So if you could just very shortly list up all the parameters you've investigated pretty nicely, and then I want to talk about some parameters we've missed in this.
Yeah, so we varied first for the angular velocity, as I just showed you. We varied the insertion depth. We varied the radius.
Yeah. Okay. And let's move to the submersion depth. If you can show us this theoretical and experimental data.
Yeah, I can. 1 second.
On the one hand, so if I understand, you're fitting here the friction factor, right?
Yeah.
Okay. Even though later on you're calculating it. The pressure.
No, the problem with the other friction calculation is that it only calculates friction for the outermost loop, because that's the most important, because that's the fastest. So we in the friction calculation I showed you a bit earlier, we only calculate the friction in the outermost loop, and to calculate the general friction inside the whole system, we would need to do a lot more calculations, which would be very intensive for like just computers and everything.
So in general, your theoretical approximation is sufficient, but we still see that, especially for low radiant and beginning for less higher submersion, that it's not working as well. Therefore, my question is now: you're additionally already fitting one parameter to this theoretical approximation. Why are you then not even hitting the trend? What effects could play a role in this? Especially considering if we have a very high immersion depth and almost the whole pump is already completely submerged into the water level.
First of all, I don't think you can really submerge the whole pump into water experimentally, because like we have the excess of rotation and it's quite hard to move it under the water.
Yeah, but I mean it would be possible to just use silicon and just to dicht up.
Yeah, but I think that's not really. I don't see why you do this. So.
Why do you believe you're still not hitting always the right trend in your theoretical approximations? What effects are you detecting?
I'm not entirely sure. I think the fit is quite good, except for the very first submersion depth. But it's very possible that there wasn't enough water getting inside of the system or something.
Just move one slide further. On slide 23, we again see an additional pattern that we have for low radii, not fitting theory, and in general this is already not completely the same trend. As you can see, you're always slightly predicting increasing radii, you're predicting more and more downwards.
I mean, it could be that I didn't fit the friction factor good enough, or that the measurements are just not perfect. So I don't know. I think the fit is quite good. So.
Okay. I believe this is due to the, as I already stated, the additional friction you're not considering in your model because the Darcy-Weisbach equation is not applicable.
We didn't use the Darcy-Weisbach equation in calculating this theoretical spaces. It's just for, as I already said, it's just a limit of a theory. The Darcy-Weisbach equation that I used only calculates the friction inside the outermost loop.
Okay, I see.
And to apply it to everything, it would be a lot more calculation intensive.
So then we come back to the same question as again, the frictional consideration of theoretical modeling. Thank you very much, Simon, for your nice conduct here. And in order to conclude this opposition now, we've talked a lot. We've talked about the experimental setup, considering the angular velocity. We've wished for sometimes a bit more parameter investigations and a bit more depth into the theoretical modeling. But all in all, Simon did a great job here. Thank you very much.
Thank you very much for this vivid discussion. Now we can go on to jury questions. Who wants to go ahead? Maxime, please.
To the opponent, you talked a lot about missing parameters. In your opinion, what are the 3 most important parameters the presenter missed in his presentation?
I've wished for a deeper investigation, especially from the angular velocity for very high cases, if we have more turbulent effects. And on the rest of the parameters, I especially wish for deeper insight how the theoretical and experimental data are not correlate.
Okay, Endre?
So to the winding number, also how many revolutions you have, what do you think would happen if you take not just 4 but 12 windings? Will you get greater heights?
Yeah.
And is your on slide to the presenter on slide 18? Can you just go there?
Yeah.
This delta phi. You meant that delta phi is a constant. Is this still applicable if you have many windings?
That would depend on the difference between the radius of the innermost winding and the outermost winding. If you wind like up to the very center, no, but we never roll it that tight because it just makes all calculations. We need to include the Archimedean spiral, and the calculations just explode. So it's very, very hard to numerically solve that.
Hakim?
To the reporter, the opponent mentioned inertial effects. Can you think of a spiral geometry for high angular velocities where centrifugal forces are not negligible?
Sorry, I didn't...
Negligible.
I can't think of one, I think. If you turn it very, very, very fast, like as I showed the edge cases, the plugs move with the pump, so then the inertial force will play a greater role, I think, if you mean that.
Same question to the opponent. Do you think that centrifugal forces are completely negligible for all spiral geometries?
No, not for all spiral geometries, because for very high radii, it could be happening at the water, or either the air gets pushed outwards, and therefore the air bubbles could push inwards further, and therefore the pumping height will not increase.
Thank you. Ottmar has a question.
Connected with Andrew's question, if you increase the number of turns, would there be a limit to the maximum height, and what factors would limit this maximum height?
I don't know if there would really be a limit in like realistic ranges. I can't think of any real reason why, I think.
Yes, I would agree with him, but I think the number of windings is also slightly determined. I mean, the combination between radii, outer radii, and inner radius of the spirals is important.
I think Endre wants to follow up on this.
Oh, actually, I wanted to change that a little bit. So suppose you have tube that goes up is of bigger diameter, okay, than the tube that the pump. What would you expect? Is there a difference in the pumping height?
For different areas of the. Yeah, I would assume because if the rest stays the same, then the height of the airlocks gets increasingly smaller, and therefore hydrostatic pressure changes because then the volume just fills up. Therefore, the height is smaller.
So the question was if you just increase the diameter of the, I think it's called the hydrostatic paradoxon, which basically says that it doesn't matter.
Okay, thank you very much. That was the last question. Now it's time for grading. Last decision, plus 0.1, minus 0.1, has to be decided now. Okay, I think everyone has decided. So please prepare your grade for the reporter, and once everyone has it prepared, you can hold it up. Okay, I think now we can see the mark for the report, please. We have 8, 8, 7, 7, 8, 7, 8, 8, 7, 7. So again, very uniform. Please give a round of applause for the reporter. And now for the discussion. What do we have? We have 9, 8, 7, 9, 9, 9, 9, 8, 7, and 8. Thank you very much, and a big round of applause. Okay, so now for some justifications. Maybe Felix can comment on the 7, although it was very uniform between 7 and 8. Sorry, we have too many Fs in here, too many Felix. The other Felix can comment on a 7 for the report.
Sure. The task stated you should have considered the pumping height, and you only considered the pressure you measured inside of your experimental setup, and that's why I gave a 7.
Okay, thank you very much. Yes, Endre wants to add something.
If I might add, because there's a difference. If you make only pressure measurements, you lose the air bubbles in the height that and how many air bubbles stay in there and increase the final height depends on the rotation rate. And I was not sure if you went to this point with your rotation rate, but.
Okay, Jonas, maybe you would like to comment on your 8.
Yeah, I quite liked your theory and your style, so basically it was amazing for me.
Okay, thank you very much. Now it's time for the discussion. There we have, for instance, Maxime. Can you comment on your mark?
Yes, I gave you a rather low mark because you started your discussion basically suggesting your topics for the entire discussion, which were missing parameters and the comparison of the theory to his experiments. And then later, you didn't really follow up on it enough. I also asked you about missing parameters, and you came up with one of them, which he actually investigated. At least he proposed a limit for the upper bound. And for the theoretical comparison, you really didn't give a suggestion of how to improve this type of fit between theory and experiment, but rather just suggested it should be investigated in some way.
Okay, thank you. And now it's time for the other Felix to comment.
So yeah, I gave you a 9 because you attacked the gaps in the theory, and I think I agree with Andre that maybe there is some more that should be investigated with a connection both to the friction and the rotational velocity.
Okay, thank you very much. Let's give a last round of applause for this fight. And again, we have a very speedy break for bathroom drinks and reshuffle. Nothing more. there. So let's get started. Take your seats for the very first physics fight of the 12th GYPT. And we now have the problem magnetic assist presented by Benedikt from Lörrach, from the Phenomenon, from the team Imperium. And then we have the discussion, which will be held by Elisa from Under Pressure. And now I wish you a nice fight. We will start your preparation time, but whenever you are ready, you can get started. And your microphone will be also switched on as soon as I stop talking.
So I think I'm ready. So hello everyone and welcome to my solutions about this year's problem number 9, the magnetic assist. I'm Benedikt from the Phenomenon, and let's start with the task. The task says attach 1 or 2 magnets to a non-magnetic and non-conductive base, such as they attract the magnet suspended from a string. Investigate how the motion of the moving magnet depends on the relevant parameters. So at first the task tells us that we have to use a string, magnets with opposite orientations, and a non-magnetic and non-conductive base. So I brought a video with me to demonstrate how these motions can look like, where I pointed in the magnets where we can see 3 main motions, one with large amplitudes, then a second motion with smaller amplitudes between the positions of the magnets, and then a third movement with small amplitudes above one magnet. Then further on, the task tells us that we investigate the motion, where we once have the torsional and the spatial movement of this swinging magnet. Then, depending this on the relevant parameters, we have the pendulum properties, being the starting position and the string length, and we have the magnet properties when using electromagnet. We have the current, the magnetic moment, position, and the number of the magnets we use. So for the task giving no limitations of the arrangement of the magnets, we choose them to be within position angle alpha and a distance from the center d, as you can see in this graph right there. So further going on, I will talk about my qualitative explanation and then my quantitative theory. Then we have a look at my experimental setup and my preliminary experiments. Then we have a look at my results and then draw a conclusion. So starting with my qualitative explanation, we first have a look at the normal damped oscillator, where we only have a gravitational and the friction force acting on the system. By looking at the potential energy graph over time, we see how the energy of the bob drops, and then coming to the rest at its energetical minimum. Now adding 1 or 2 magnets to the system, we also add 1 or 2 potential energy minimums to the system, and of course a magnetic force. Further going on, by now looking at the energy of the bob over time, we can see 3 main phases. One where the energy of the bob is so great that it exceeds the influence of the potential energy minimums. Then a second phase where the energy of the bob dropped, and now we have a great influence of those potential energy minimums. And then a third phase where the energy of the bob is so low that it's mainly defined by the magnet. By looking closer at this, we see that it is actually very similar to a normal damped oscillator, and then again coming to the rest at its energetical minimum. So for our quantitative theory, we first have a look for the spatial movement of all the forces acting on our swinging magnet, where we have the tangential parts of our gravitational, damping, and magnetic forces, which we can then take in count by projecting these forces on our normal vector n. Then further going on with these definitions for the magnetic and the damping force, and the magnetic force being the negative gradient of our potential, since we have here a conservative force, we get this following differential equation for our spatial movement. The same thing we do for our rotational movement, where we look at all the torques acting on a system, where we have the torque due to the string, the damping, and the magnet, and then again here taking only the ones in movement direction. So with this, we get this following differential equation for our rotational movement. Now we have these 2 differential equations, where we still have to characterize these 3 red values and still have to be modeling our magnetic field. So let's start with that. For the modeling of our permanent magnet, we assume it to be rotational symmetric around z-axis and describe it with a dipole-dipole model, where we have the magnetic moment as a material constant. Then for the modeling of the electromagnet we used, we model it as a helix with a radius r, the height h, the number of windings n, and a position on the xy plane, where we get to this following parametrization of our electromagnet. Then further going on, using the Biot-Savart law, we can describe the infinite part of our B field from the infinite part of our length of the current, and then by using a line integral, we can get to this following equation for the B field of our electromagnet. Then plugging this into this differential equations from before, we get to these 2 differential equations for the spatial and torsional movement. So now let's go on to our setup. For the setup, we use an all-wooden frame and board, so we have no magnetic interaction. Then we use the starting fixture, as you can see in the picture right there. So we have a free swing and can reproduce our measurements, and we use the breadboard with pins to control the position of our magnets from the bottom. So for the filming, we use the camera from the top, where we then film through in plexiglass where the magnet was fixed. On top, we had the ring light, which then acts as high contrast on those two colored markings which we put on top of our magnet in order to track the torsional as well as the spatial movement. So I brought a video in to demonstrate how this can look like, where we can set these 2 points for calibration, then the next 4 points for our coordinate system, and then automatically track the rotation and the position of our swinging magnets. Now, coming to our preliminary experiments, we first wanted to characterize the magnetic moment by measuring the flux density around every room direction, and then fitting dipole-dipole model in order to get to our magnetic moment. For the spatial damping coefficient, we let the magnet free swing without any magnetic interaction, and then fit it with the regression of amplitude, and this in an exponential fit. Then for the torsional damping coefficient, we did exactly the same. We let the torsional motion free swing, then fitted the regression of amplitude, and then determined the torsional spring constant with the periods of time. So now, starting with my results. For the results, we first have a look at the polar and torsional angles theta and beta over time, where we can see in generally agreement in the amplitudes and in the resting position for both the spatial and the torsional movement. But out of this graph, we get no much more information about the actual behavior of the pendulum, so we further started investigating and looked at the oscillation periods of those movements, where we have here the spatial and the torsional movement. Here, we can see 3 main characteristic phases. One, a first phase with increasing periods of time till we have a local maximum, and then rapidly decreasing oscillation periods in the second phase, and then nearly constant oscillation periods in the third phase. The same thing we can observe by looking at the torsional movement, where we have here the experimental data in smooth, and where you can see that we have the same transitions for the third phase, and that again we have here a nearly constant oscillation period time. So we have 3 phases of motions, and they both match up in both of the movements. So we now further wanted to investigate those phases, starting with them qualitative, where we have a look at the first phase, where we can see the trajectories, and the phase space, where we can see that we have large amplitudes, since the energy of the bob is still high, and we've got a deflection of the linear movement. And looking at the phase space, we see this ingoing elliptical attractor, which speaks in this case for an almost no magnetic influence, and the motion of the pendulum is here mainly defined by its gravitation and damping. Then when the energy of the bob drops due to damping, we see this movement in the trajectory. We have a more complex movement between the position of our magnets. And then again, looking at the phase space, we see then we have actually this like H-shaped attractor, where we have, which talks for an acceleration towards the position of our magnets, which in this case seems to be that we have mainly a magnetic influence and the behavior of the magnet is mainly defined by the position and strength of our magnets. Then coming to the last phase, where we look at the trajectory again, where we can see those small amplitudes above the resting position, since the energy of the bob dropped due to damping even further. And again, looking at the phase space, we see this ingoing elliptical sphere, which in this case then talks for an almost harmonical oscillator due to the small changes in position of the force. Here we have mostly magnetic influence. Then further going on, we investigated the transitions of the phases. So when does these transitions happen? So we investigated this over the starting angle psi, where we can see that with an increasing starting angle, so an increasing in starting energy, we also get and slower transitions from the first to the second phase. The transitions for greater starting angles from second to third phase actually stay the same here. So then going on to the transitions from the first to the second phase over the current of the stationary magnet and the distance from the center, where we can see that we have generally faster transitions with greater currents at the magnets and greater distance. The same thing we can observe by looking at the transitions from the second to the third phase, where the most interesting thing is that actually these transitions, as I told earlier, from the torsional and spatial movement match up with each other. Now, further investigation, not only the transitions of the phases, so we wanted to further investigate the resting positions and frequencies. So starting with the frequency in the third phase, as I told earlier, we have a nearly harmonical oscillator, and then when modeling our electromagnet as a dipole, we get to this equation for our force, which is then only depending on the distance, which we get to this easier differential equation, which has an analytical solution. And by looking at what this analytical solution looks like, we plotted this over the length of the string, where we can see that we have an increasement in frequency with an increasing in length of string, and that for smaller length of string, this analytical model actually predicts very well. And further going on, we investigated the resting positions above the current as a stationary magnet, the distance from the center, the position angle. And the main thing we see is that the magnet just moves along. So we have the same resting position as the position of the stationary magnets, but we see some more interesting cases, which I want to be talking more about, where we have this last jump in our graphs, which then can be explained by looking at the potential over this axis, where we can see that when the magnet is actually too far away, we have no stable equilibrium where the magnet can come to and rest. The same can be observed when looking at when the magnet is actually too strong, then we have no stable equilibrium anymore, and we come to the rest at the position of the second magnet. Talking about stable equilibriums, we further investigated those by looking at some different correlations of distance and strength, where we can see that we have up to 3 different stable equilibriums. And these we investigated then with simulations about our fractal basins of attraction, where we always looked where the magnet comes to rest. Here a red pixel means we come to rest at the first magnet, same for the blue. And what we can generally see that we have a stable regime where it's symmetrically around the center, and we have a sensitive regime where we actually, with small changes, get to whole different positions. These we investigated for all the parameters I listed so far with over 300 simulations. I can talk about that later in the discussion, since I have no time left. We draw a conclusion now what we did. So we built a sophisticated setup with automatic video tracking. We've done precise experiments and characterization for errors, and we've derived an accurate theoretical model. And for the task fulfillment, I investigated both the spatial and torsional movement over all these parameters with their phases, behavior, frequencies, and resting positions. So thank you very much for your attention. Looking forward to a pleasant fight.
2 minutes preparation time. Just a reminder, please stay quiet.
So first of all, I would say thank you to you. It was a very fascinating report. You had very good points, so I really liked your experiments you did and your structure. But I have got a few things just to discuss. So at the beginning, could you please go to the task?
So the task is, if they reach that.
So here it is said that they attract. Yes. How can you ensure that they really attract it every time?
So they have
so with your experimental setup.
So I mean they had opposite orientation. In order for them to be not attracting, the magnet had to be flipping around 180 degrees, and with angles about 10 degrees, I'm quite sure that didn't happen.
Okay, that's just for the beginning. So now I want to come to your experimental setup.
Sure.
So you didn't really talk about how your magnet is fixed or how your string is actually fixed.
So the fixture, sorry, here it is. You mean the stationary magnets or the swinging magnet?
The swinging magnet.
So on top of on the plexiglass plate, we did a hole in there and fixed it with hot glue. So it's only and then we measured the distance from the length of the string at the point where the where the string comes out of the hot glue, and for the part of the swinging magnet, as you can see here, we used a little 3D printed plate or something where we then glue the string in.
To the string, so where you fix it with the glue, is there any friction there? Because if you just fix it, or does it have an impact?
So I think it could have a small impact, but all of the friction, which is due to the fixture of the magnet, is within the fit of in my damping coefficient. So I let the magnet free swing with exactly this combination, and then this is actually in our damping coefficient.
Yeah, okay, I agree with that. And how you can also ensure that there's no torsion?
There is torsion, and I measured the torsion.
Okay.
Or do you mean the length contraction due to the torsion? Yeah. So yeah, I thought about that when we use different strings, but in this case I only used a plastic string, which has only one string.
Did you always use the same string?
I have always used the same string.
Could you imagine what would happen if you use another string and other materials? For example, if you change the elasticity of the material?
So I think the elasticity of the material doesn't have such a great impact. I think the only impact of the string would be when due to the high torsional, so when we have around like 2 rotations, that the length contract of the string actually gets relevant.
So I would say that actually I think, in my opinion, elasticity plays a role.
What do you think? Would it have a qualitative effect on the motion?
Yeah, because it can expand, and I think this can also maybe change the motion.
Yeah, that's what I state. When the material of the string has an impact on the length contraction, then I would agree to you that it has an impact on the motion, since a distance from the magnet is changing. But when only looking at different movements, then I would say there's no impact.
And you talked also about the length, and how is the motion changing if you actually change the length?
So what part of the motion? I mean, the resting position doesn't change. The resting position of the motion doesn't change. But I mean, I showed how the frequencies of the motion in the last phase, for example, decrease, if that's what you want to talk about, this plot.
Yeah.
So, I mean, yeah, you can clearly see that with an increasing length of the string, the frequency decreases. So I derived this analytical model for this last harmonical phase, and generally you can see that it agrees with our measurements, but here on this last point, there we seem to have a disagreement. I think this is because when I use a very short string, then my angles, so my small angle approximation isn't really applicable anymore.
Yeah,
I calculated the error for that, and this is actually exactly the error.
Yeah, that's what I also think. Okay. To your theoretical model, so you talked about the dipole moment.
The dipole moment, yes. So
and
show it.
Yeah.
What this? Dipole model?
Yeah. So if you use the dipole model, actually you need to use a point dipole, and you just have here an approximation. So here you're using a cylindrical. So I think this here is
no, it is.
That it changes actually.
Yeah, I see what you mean, but this is actually theoretically described as a point dipole with the dipole model.
I think this is just an approximation here.
Yes, it is an approximation. Do you have a suggestion how you could do it with another model to do it better?
Yeah, so I think that would be very complicated, of course. So I think you would need another theoretical model.
I also thought about using Biot-Savart. You can also apply Biot-Savart for permanent magnets, but we tried it, and there's no better better prediction with then using the Biot-Savart. So the simple model actually worked as well. So we stayed with the dipole model.
So with that you got better results with the dipole model.
No, I didn't get better results. They were actually very much comparable.
Okay. Let's come to your comparison of your theory and your experiments.
Sure. What do you want to compare? The transitions, the resting positions?
So, for example, on slide 32.
32?
Yeah.
This one? Yeah, sure.
Here you have a very high difference at time 45 seconds to your theory and experiment.
Sure.
So why is that actually?
So in the spatial movement, over the second time we see a disagreement in the frequencies. And I think this is because there's actually not only the torsional movement, but also the magnet. I don't know how it's called. I can explain it to you by drawing. Yeah, sure. So when you have this pendulum with the magnet, and this also tilts around this angle here when it gets closer to the magnet. So when you have the magnet here, it tilts a little bit in this direction. And this effect gets very strong, of course, when we have a fast movement between the magnets. So I think that this could be the influence which we can see in the second phase here, getting to this disagreement from the frequencies.
And why then, okay, yeah, so that's also for the same with 100 seconds. Because here you have a higher
the disagreement stays the same, the disagreement stays the same.
Okay, I would also say that it's because of this fast motion. Also on slide 35.
35, this one, yes.
You got those experimental and theoretical results.
Yes.
So would you say that you kind of like mentioned it, but is it chaotic behavior?
I didn't mention any chaotic behavior.
So would you say that it is?
I think it's a good question. I would say that the motion in the second phase of the two magnets, I would say that I haven't investigated it, but I would say it isn't what.
Investigate it?
Would you say that is chaotic?
I would kind of like say it because we have discrepancies between the theory and the experiment.
And then how do you define chaotic when this is chaotic in the
So I think you can't really predict what's happening next time. Or
I would disagree on that. That is the definition of chaos. So I think, we can move to another point because I don't disagree with that.
Okay.
I disagree with that.
Also, to the next thing. So you, in your experiments, you only used one magnet.
No, I used 1 and 2 magnets. I showed the results.
Can you show the comparison again, please?
So this is the comparison. So this is the trajectory for 2 magnets.
Yeah,
I focused on the report with 2 magnets because it's the more interesting case. But if you want to talk about 1 magnet, sure.
Yeah.
I can show you the measurements. Shortly going to my appendix. This is the comparison of the trajectories for 1 magnet when they are aligned in the moving direction. Or do you mean about the resting positions? Because those are the measurements for the resting positions with 1 magnet.
Okay. So you investigated both?
I investigated both. Since I stated I investigated a number of magnets.
And where are the most differences between if you use 1 magnet or 2 magnets?
Yeah, I mean in the motion, I mean when I have only 1 magnet, I have only 1 energetical minimum, which I add to the system. where the magnet is referring to. Of course, the resting positions can only come out by only one magnet. So all of this fractal basins of attraction, which you can see here.
Here I have a question again. So you talked about basin and about fractals. So how can you make sure that those are really fractals?
I don't understand.
How can you really investigate that those are fractals?
So what do you define by those fractals? So I investigated how the resting positions changes with different starting positions over different over different positions and strengths of our magnets. So I don't see what is your question.
So could you describe it with a fractal, for example?
I don't understand the question.
Okay,
so
I think we don't come to a point here.
Can you explain to me what you mean by this question?
So I think we have to end up, because we need to conclude. Actually, we talked about the experiment setup, and I think maybe you could change a few things again. You could also investigate how the elasticity plays a role in your model, and also investigate how the fractals, but you didn't really get my point. Maybe we could talk about it afterwards. Thank you very much for your discussion.
Thank you.
Thank you for this nice discussion. So now it's time for the jury questions. Who wants to start? Cosmos wants to start.
To the presenter, can you please go to one of your potentials? It's irrelevant which one. You have a 2D plot here, but we have a 3D potential.
Yeah.
So where do you draw your line? So what is the cutout?
So when we variated the distance from the center, we always had the magnets in starting direction, so the line cut was actually on the starting direction, on the movement direction axis. Same for the other plot.
Do you think it is possible to do a 3D diagram for this problem?
Yeah, of course. I have some 3D diagrams, but only with the view on top. Shall we look after it? Sorry. So appendix. So here. Those would be then the 3D graphs.
Thank you.
Sure.
Then Hakim.
I would state that the starting velocity wouldn't have a great impact when changing the so I would have the same impact when I increase the starting angle on the motion of the pendulum. So I investigated this as a several parameter.
Then Endre is next.
Yeah, can you please go to slide 35?
Sure.
There you show the comparison between your theory and the experimental data.
Yes.
And have you also a plot of this for short times, shortly after releasing your pendulum by hand?
Yeah, this is, I don't know how you call short. This is the trajectory 15 seconds after releasing.
Yeah, but I mean, those 2 seconds, just the first 2 seconds or 3 seconds. So how fast those two are diverging, because there are quite some differences between the theory and the experiment there.
No, I haven't investigated those first seconds.
Okay, yes, Ottmar, next.
Can we have a look at slide 19? It's about the dependency of the flux density on the R.
Slide 19, sorry?
There was a sketch also with your measured data.
So 19?
Yeah, the next one probably with the plot.
fit since we use a different model. But with lots of measurements, I don't think that the change in the actual magnetic moment that we fitted would be very great.
Cosmas, quick question.
Very quick for the opponent. You talked about the wobbling of the magnet. Do you have
Okay, 5 seconds to answer.
So you could add something to the magnet in order to get how the move is done. How the motion is.
Okay, thank you. So that were the jury questions. Now it's time for grading. Please, quiet, thanks. After this fight, you will have time to discuss. Okay, last decision has to be made. Okay, I think we are done now. Please prepare your mark for the presentation. Everyone prepared? Good. So hold it up. We have 9, 9, 10, 9, 9, 9, 10, 10, 9, and 10. So congratulations on that high score. Now we have a look for the mark for the discussion. So hold it up, please. We have 7, 6, 6, 6, 8, 7, 8, 7, 7, and 7. Thank you very much. So for the report, we had such a good and uniform grading. Whoever wants to come forward can comment. I don't want to pick anyone out. Yes, Cosmas?
So I really liked your report. You had a nice setup. You did very good experiments. You designed your model. You modeled it also in 3D. That was my question. And so you had an overall good theory, good experiment, and they were nicely put together.
Second comment, maybe? Yes, Felix.
Overall I agree. I gave you 9 points and not 10, mostly because you did most of your theory in numerics, right? You numerically solved it all, so I think it wouldn't have been that much harder to also include parameters like this tilting, which could have accounted for some discrepancies, which 10 is a perfect report, so for it to be perfect, things like this would have been included. So, but it's almost perfect, and that's great.
Okay, thank you. Then for the opposition, we have a 6, for instance, from Ottmar, I think.
Well, I really liked your calm and polite presentation style. Nevertheless, you should be more attentive on the real physics behind. You spend a lot of time, I think about 5 minutes, about the experimental setup. In my opinion, it was quite clear. On the other hand, I would like to propose us some suggestions, some improvements on the experiment, and maybe what could be else investigated that I was missing a little bit.
Okay, and then we also have an 8, for instance, from Thomas. Can you comment?
You brought up very interesting topics like the suspension or the onset of chaos, maybe, and your discussion structure was very well structured.
Okay, thank you very much. Is there anything to add from anyone? No. Okay, I think then I will head over to the organizing team. Thank you very much for this fascinating fight.
Genau, wir switchen wieder auf Deutsch. Der offizielle Teil des Finales ist vorbei. Wir machen eine 15 Minuten Pause, also wir treffen uns 11:30 Uhr wieder hier. Bitte seid pünktlich. Genau. Oben gibt's Kaffee. Wir sehen uns gleich hier zur Preisverleihung. Genau, bevor wir zu der eigentlichen Preisverleihung kommen, möchte ich noch ein paar Worte des Dankes sagen. Es haben an diesem Wochenende ganz, ganz viele Menschen gearbeitet, aber ich möchte jetzt vor allem denen danken, die ehrenamtlich gearbeitet haben, weil das ist, glaube ich, einfach nicht normal, nicht selbstverständlich. Da ganz vorne voran unsere große Jury, Lehrkräfte, Profs, Studierende der Physik, die sich hier das Wochenende um die Ohren geschlagen haben, teilweise 12 Fights gestern nacheinander juriert haben und das alles ehrenamtlich. Vielen Dank erstmal an die Jury. So, dann hat ehrenamtlich dieses Wochenende ganz viel Sebastian mitgeholfen im Office. Ich weiß nicht, ob ihr ihn so oft gesehen habt, aber er hat uns so viel Arbeit abgenommen im Office. Vielen Dank, Sebastian. Und dann, ihr habt ihn wahrscheinlich auch mitbekommen, macht die ganze Zeit Fotos. Felix Wechsler hier oben wird hier auch gleich Fotos machen. Und auch nicht so ganz sichtbar, aber die haben auch schon sich vorbereitet die letzten Tage, die beiden Bitschig-Brüder, die den Livestream hier organisieren. Vielen Dank auch an euch. Okay, dann kommen wir jetzt zum richtig spannenden Part. Wir fangen hinten an bei den Bronzemedaillen. Die wisst ihr ja noch nicht, das weiß noch niemand außer wir. Das ist spannend für alle. Ja. Doch jetzt. Okay, für die Bronzemedaillen ist unser lieber Herr Laudator, der Herr Dr. Stefan Jorda. Er ist der Geschäftsführer der Wilhelm und Else Heraeus Stiftung, die dieses ganze GYPT vom Regionalwettbewerb, Bundeswettbewerb bis zu den internationalen Wettbewerben, also unsere Teilnahme an den internationalen Wettbewerben finanziert. Vielen Dank, dass du da bist und ich würde damit dir die Worte übergeben.
Ja, ich halte die Spannung noch einen Moment. Ich will, bevor ich den Zettel brauche ich auch gar nicht, bevor ich jetzt die Bronzemedaillengewinner verlese, möchte ich noch ganz kurz ein paar persönliche Worte sagen. Es ist mein 10. GYPT. Seit 2016 war ich jedes Jahr hier als Juror. Ich komme wahnsinnig gern hierher. Es macht mir immer total viel Spaß, dieses Physikzentrum ein Wochenende lang gefüllt mit Schülerinnen und Schülern zu sehen, die sich für Physik interessieren und hier diese spannenden Fights abliefern. Für uns als Stiftung ist es wirklich ein Aushängeschild, dieser Wettbewerb. Wir sind auch stolz darauf, dass wir diesen Wettbewerb finanzieren. Wir geben dafür im Jahr zwischen 150.000 und 200.000 Euro aus für dieses GYPT hier, für die Regios, für die internationale, für die Teilnahme am IYPT. Und ich denke, das ist super gut investiertes Geld. Aber mit dem Geld allein ist es eben auch nicht getan. Deswegen knüpfe ich gerade direkt an das, was du gerade gesagt hast, mit ein paar Worten des Dankes. Es sind hier wahnsinnig viele Leute engagiert, angefangen mit euch, mit dem Orga-Team, mit all diesen Leuten, die im Hintergrund dafür sorgen, dass hier der Wettbewerb organisatorisch und so weiter läuft. Aber natürlich sind hier auch wahnsinnig viele Betreuer vor Ort in den GYPT-Zentren an den Schulen engagiert, denen es immer wieder gelingt, Schülerinnen und Schüler dafür zu begeistern und zu ködern, dass sie eben anfangen, hier zu sich da zu engagieren, ihre Projekte zu machen und hier dann zu kommen. Und ich hoffe, dass unabhängig davon, ob ihr jetzt gleich hier vorne steht und eine Medaille gewinnt oder nicht, ich hoffe, dass all diejenigen, die hier waren, beglückt und freudig nach Hause gehen und einfach ein tolles Wochenende hatten. So. Jetzt kommen wir also zu den Bronzemedaillen. Mit 42,54 Punkten hat eine Bronzemedaille das Team Newton's Apples aus Meißen bekommen, das aus Kalina Pahl, Jara Pfeiffer und Paula Wiluft besteht. Soll ich sie erst alle vorholen oder machen wir? Ich glaube, es ist... Ja, nee, dann machen wir es. Also wir halten die Spannung mit den weiteren und überreichen jetzt so. Also herzlichen Glückwunsch, jetzt gibt es eine Medaille. Okay. Das ist das jetzt dann für wen? Na, wir machen das unabhängig mit den Medaillen und mit den Preisen. Herzlichen Glückwunsch.
Einmal für dich.
Und nochmal eine Medaille. Übergibst du das dann? Und jetzt gibt es hier noch, ups. So, herzlichen Glückwunsch. Bleibt ruhig noch hier, ne? Dann gibt es ja hier noch Gruppenfotos. Ebenfalls die Bronzemedaille mit 42,74 Punkten bekommt das Team Betrag von X aus Dachau. Mit Mihailo Matsiewicz, Nikita Petrov und Ayush Yadav. Herzlichen Glückwunsch. Ups. Bitte schön. Herzlichen Glückwunsch. Und dann macht ihr das? Gibt es noch die Buchpreise dazu? Und als drittes Team mit einer Bronzemedaille mit 43,63 Punkten gewinnt das Team Bongo Bosos aus Berlin mit Bella Kellerer, Kerem Semis und Vito Somani. So, ich fange wieder hier an. Ganz herzlichen Glückwunsch. Glückwunsch. Ja, wunderbar. Und dann gibt es noch die Buchgeschenke dazu.
So, vielen Dank. Foto haben wir schon gemacht. Wir kommen zu den Silbermedaillen. Die Teams habt ihr schon gesehen, gerade im Finale. Wer mitgerechnet habt, ihr habt ja auch die Noten gesehen, ist es vielleicht nicht mehr ganz so überraschend. Nichtsdestotrotz natürlich wichtig. Herr Runge steht schon da. Professor Dr. Erich Runge ist bei der Deutschen Physikalischen Gesellschaft, die ja die Veranstalterin gemeinsam mit der Universität Ulm ist, des GYPTs ist Vorstandsmitglied für Bildung und wissenschaftlichen Nachwuchs. Vielen Dank.
Also für mich ist das der erste GYPT und ich bedanke mich ganz doll bei den Teams. Das waren unglaublich entertaining Fights. Also ich habe die 1,5 Tage genossen. Ich bewundere und bedanke mich bei den Committed Standortleadern, also ich bewundere sie auch. Es ist toll, was sie gemacht haben aus den Teams. Ich kann es mir vorstellen. Also super gut. Die Organisatoren waren auch gut, aber die habe ich wenig gemerkt, weil es einfach so gut geklappt hat. Insofern vermute ich mal, dass die auch super gut waren. Also wirklich vielen, vielen Dank für den Entertainment. Für das Entertainment, was ich gehabt habe. Warum ich hier stehe, hast du ja zum Teil schon gesagt. Zum Teil auch, weil in der DPG der eine oder die andere weiß, dass ich früher im Wettbewerbe mag. Ich war früher lange Jahre Trainer von der Mathematik-Olympiade, der Westdeutschen Mathematik-Olympiade und Bundessieger im Bundeswettbewerb Mathematik, bevor es mich in die Physik verschlagen hat. Und was ich witzig finde, damals, wenn man Bundeswettbewerb und Olympiaden vergleicht, da sind unterschiedliche Leute, unterschiedliches was rausgekommen. Wir hatten nach der Wende mal so ein deutsch-ostdeutsches Wiedertreffen, weil ein Ministerpräsident war ehemaliger Olympionik auf der Ostseite. Und da habe ich eigentlich festgestellt, die Mathe-Wettbewerbleute waren mehr die später mal Mathe-Professoren wurden. Und die Mathe-Olympiaden waren oft auch so Ministerpräsident oder Firmengründer oder sowas. Also das sind doch andere Qualitäten. Und natürlich hat mich das ja zum Rätseln gebracht, was aus ihnen so wird. Ja? Und ich bin jetzt Physikprofessor, deshalb muss ich jetzt bei uns in Ilmenau Physik-Olympiadetraining machen, habe ich mir gedacht. Und mach das auch. Und habe da immer erzählt, die Mathe-Olympiade-Aufgaben sind eigentlich lustiger irgendwie. Ich habe mich entschuldigt, dass ich nicht so schöne Physik-Olympiade-Aufgaben habe, wie ich Mathe-Olympiade-Aufgaben habe. Mache trotzdem Physik-Olympiade-Training und jetzt in diesen Tagen ist mir die Erleuchtung gekommen, woran das liegt wirklich. Dieser Wettbewerb hier, das sind diese nicht definierten Fragen, die trotzdem irgendwie gut definiert sind und wo man nachher gute Antworten hat. Brauche ich Ihnen vielleicht nicht erklären. Mir war das aber, also mir ist eine echte Erleuchtung, dass das eigentlich das wirklich Physikwesen ist und dass das ein Unterschied zu Mathe ist. Und dass dann logischerweise ich hier ganz viel, was ich bei den Physik-Olympiade-Aufgaben immer vermisst habe, es gibt wenig Aufgaben, die ich weitererzählen will. Bei Mathe-Olympiade, ich weiß nicht, wer Mathe-Olympioniken kennen, treffen sich zwei auf dem Flur, fangen sich an, sofort Aufgaben zu erzählen gegenseitig, wie schöne Aufgaben das sind. Habe ich bei Physik-Olympiade-Aufgaben irgendwie weniger erlebt. Hier habe ich jetzt Aufgaben erlebt, die ich sofort weitererzählen will. Ja, also das ist für mich eine echte Erleuchtung, dass das vielleicht der richtigste Wettbewerb ist und deshalb frage ich mich natürlich, was aus Ihnen alles so wird. Ich vermute mal mit dieser Mischung aus intellektueller Brillanz und Kreativität und dann noch Teamfähigkeit, ist eigentlich der Himmel offen und der Himmel ist für mich natürlich Professorin zu werden. Deshalb vermute ich, dass der eine oder andere von Ihnen Professor wird. Bin ich gespannt draus. Was Sie sich beibehalten sollen, was im Unibetrieb mir auch aufgefallen ist, was leider ein bisschen zurückgeht, ist, was Sie toll machen, Sie hören sich gegenseitig zu. Also die Opponenten hören dem anderen wirklich zu und ich muss leider sagen, dass auf Konferenzen würde ich in Zukunft, wenn ich oft dran denke und würde sagen, hätten die mal ein GYPT gemacht, würden sie den Vortragenden zuhören, anstatt nur eine Frage zu stellen. Ich will nur sagen, ich bin auch hier und ich bin noch viel besser. Ja? Also behalten Sie sich das bei, werden Sie Professor, werden Sie Professorin oder werden Sie auch was anderes, aber mir haben Sie Spaß gemacht, ich habe viel gelernt und werde überlegen, ob ich nicht von Physik-Olympia-Stützpunkt Ilmenau Richtung GYPT gehen muss, um echte Physiker auszubilden. So. Nach dem, was ich gelernt habe, in der Freude habe ich jetzt auch noch das Vergnügen, Silbermedaillen an zwei tolle Teams zu verteilen. Das eine ist Team Kurtis Knappen mit 23,1 Punkten, Simon Hermes, Ruschel Seiden, Nutal Lapati und Kurt Stiller. Kommt ihr vor? Ja, also vielen Dank für Ihr tolles Engagement und darf ich die Medaille umhängen? Seien Sie stolz drauf. Das ist toll, was Sie so gemacht haben. Auch Ihnen vielen Dank und Glückwunsch. Okay, gut. So, vielen Dank. Nee, heutzutage bei Corona und Bazillen und sowas Ähnliches hätte ich Verständnis für jeden, der nicht eine Hand reichen will. Bevor Sie weglaufen, sage ich Ihnen noch, das wissen Sie aber auch noch, dass Sie zu der Exkursion zum CERN eingeladen sind. Ja, das ist natürlich auch noch ein super extra. Also das, gut. Das mit dem CERN trifft natürlich genauso zu auf das andere Silbermedaillenteam. Große Überraschung, Ander Brescher aus Bayreuth. Ich bitte Daniel Tulgin, Elisa Schöps und Benjamin Graf auf die Bühne. Gut. Also super, darf ich mir damit zuerst gratulieren. Also vielen Dank für diese ganzen tollen entertaining Fights und was ihr alles für Experimente gemacht habt. Wie gesagt, als theoretischer Physiker stehe ich da erstaunt davor. Also Ihnen herzlichen Glückwunsch, super Leistung, Ihnen auch herzlichen Glückwunsch, tolle Leistung und auch Ihnen eine richtig rumgedrehte Medaille. Ja. Genau. Das Lachen ist noch schöner mit Applaus. Gut, und auch Ihnen viel Spaß beim Turn dann natürlich, logisch.
So, vielen Dank. Dann, ja, das beste Team dieses Bundeswettbewerbs, das Goldteam, wird präsentiert von dem Altpräsidenten der Deutschen Physikalischen Gesellschaft. 2020 bis 2022 war er Präsident und mindestens seitdem, weiß ich, ist er ein Fan auch vom GYPT, jedes Jahr dabei. Genau, vielen Dank, dass Sie da sind.
Ich nehme das Mikrofon, hallo. Ja, vielen Dank für den freundlichen Empfang. Ich habe hier also die absolute Überraschung, aber da komme ich gleich drauf. So wie die Kollegen und die Vorredner vor mir schon im Grunde genommen vieles oder fast alles gesagt haben. Also Frau Brandt, Sie haben ganz viele Leute hier erwähnt. Für mich auch ein Beispiel dafür, dass Sie stellvertretend, Frau Lorenz, Herr Steck vorne stehen, aber im Hintergrund ganz, ganz viele Leute noch arbeiten. Und man glaubt das gar nicht, wie anstrengend das ist und was da alles zu tun ist. Stefan Jorda, dir muss ich widersprechen. Geld ist zwar nicht alles, aber ohne Geld geht es auch nicht. Also der Wilhelm und Else Reus Stiftung muss ich nochmal einen ausdrücklichen Dank überbringen, vermitteln, weil, wie gesagt, ohne euch ginge es nicht. Und man muss aber dazu sagen, die Wilhelm und Else Reus Stiftung ist in der DPG, also als Finanzer würde ich sagen, voll investiert. Also sie fördert ganz, ganz viele Projekte und vieles, was wir als Aushängeschild mit der DPG verkaufen, geht ohne die Wilhelm und Else Reus Stiftung nicht. Zwei Gruppen sind meines Erachtens noch nicht erwähnt worden. Die erste Gruppe sind nämlich hier die Teilnehmer und Teilnehmerinnen. Denn ohne die ginge es auch nicht. Und ich muss sagen, ich glaube, das ist jetzt mein drittes oder viertes Mal, dass ich hier die Goldmedaille verteilen darf. Und muss sagen, ich bin immer wieder fasziniert davon, mit welchem Engagement Sie sich das Wochenende um die Ohren hauen, ebenso wie die Juroren natürlich. Aber es ist unglaublich. Und ich sage es auch immer wieder, als ich in Ihrem Alter war, habe ich andere Prioritäten, nein, das sage ich lieber nicht, andere Prioritäten gehabt. Ja, es ist schon schön zu sehen, ich komme da gleich nochmal drauf, wie Sie Interesse an der Physik haben, an der Lösung von Aufgaben, an Experimenten. Ich bin auch Experimentalphysiker und muss sagen, ich sage immer, ich habe Physik studiert und Erich, hör mal weg, weil ich nicht rechnen kann. Ja, weil das Experiment, das ist das, was reizt, zu schauen und das dann auch mit einer Theorie zu vergleichen, das macht schon Spaß. Die zweite Gruppe, die bislang noch nicht erwähnt wurde, das sind die Lehrer und Lehrerinnen. Denn ich bin davon überzeugt, die allermeisten, die hier teilnehmen, wären nicht hier, wenn sie nicht vernünftige Physiklehrer und Physiklehrerinnen gehabt hätten, die sie motivieren, sich auch, wie gesagt, das Wochenende um die Ohren zu hauen, Interesse zu haben, dass das Spaß macht, zu wissen, wie ein Regenbogen funktioniert, wie ein Wassertropfen entsteht und was dahinter steckt. Also vielen Dank an die engagierten Lehrer und Lehrerinnen. Ich muss zugeben, Ich habe auch Physik studiert, aber ich habe solche Lehrer nicht gehabt. Also für mich war das, ich war eher Spätzünder. Ich muss aber auch dazu sagen, für diejenigen, die hier keine Medaille gewonnen haben und teilgenommen haben, ich habe auch nie an einem Wettbewerb teilgenommen und bin trotzdem Physiker geworden und habe es auch nie bereut. Also geben Sie den Mut nicht auf, bleiben Sie dabei. Und ich hoffe, dass der eine oder andere, ich hoffe, dass alle Physik studieren und vor allen Dingen auch in die DPG eintreten, wenn sie nicht schon Mitglieder in der DPG sind. Bevor ich zur großen Überraschung komme, nämlich der Goldmedaille, möchte ich jetzt sozusagen die andere Seite, die Herr Runge betont hat, erwähnen, nämlich die Industriephysik. Also auch wir in der Industrie brauchen Sie als Physiker und Physikerinnen, um den Herausforderungen, die wir heute schon haben und in der Zukunft haben werden, sei es Energiethemen, sei es KI, was auch immer noch auf uns zukommt, um das zu lösen, dafür brauchen wir Ihren Einsatz, Ihren Intellekt. Und ich weise immer gerne auf unsere Studie zurück hin, wo wir mal aufgeführt haben, wo landen eigentlich Physiker und Physikerinnen. Und da stellt man fest, dass, nageln Sie mich bitte nicht fest, aber mehr als 2/3 gar nicht in der Forschung landen, sondern in allen möglichen Berufen. Jetzt könnte man ja meinen, ja gut, die finden nirgendwo anders einen Job, dann müssen die halt Berater werden. Nein, das ist schon anders. Das, was Sie lernen im Physikstudium, das sind Eigenschaften, die gerade halt in vielen Berufen gefragt sind. Das sind gar nicht mal die Fachthemen. Da spielt es gar keine Rolle, ob Sie jetzt in der Theorie promovieren oder einen Master in der Spektroskopie machen, sondern eher die Art, wie Sie sich Wissen aneignen, wie Sie an Probleme herangehen. Und das konnte man hier übrigens wunderbar sehen, wie Sie an Probleme herangehen, wie Sie sowas analysieren und dann tatsächlich, wie sagt man, den Elefanten in Scheiben schneiden. Frau Brandt guckt mich schon immer so an. Sie hat mir vorher schon gesagt, ich soll mich kurz fassen. Okay, also bleiben Sie am Ball. Ich finde das top und ich hoffe, dass ich nächstes Jahr auch wieder hier den Herrn Richter vertreten darf, weil der muss, und ich glaube, die Vorstandskollegen, die müssen auch gleich los. Es ist nämlich Vorstandssitzung in Bonn und deswegen kann Herr Richter heute nicht teilnehmen. Er hat mich gefragt, was ich gerne tue. So, jetzt kommen wir zur Preisverleihung und ja, ich bin echt überrascht. Das Team Imperium. Mit über 27 Punkten, also deutlichen Abstand zu den Silbermedaillen, haben Benedikt Baum, Johannes Hofmann und Maxim Rasch die Goldmedaille bekommen. Und ich muss jetzt das Mikro abgeben, um die Medaille zu überreichen.
Genau, herzlichen Glückwunsch euch. Vielen Dank. Genau, die nicht zum ersten Mal dabei sind, die wissen es ja. Jetzt kommt noch ein sehr spannender Part, und zwar diejenigen unter euch, die die besten Einzelleistungen hatten gestern bei der Vorrunde. Das sind 12 Menschen, die wir da gleich noch ehren, und die werden zum Auswahlworkshop eingeladen, wo dann die Nationalteams für die europäische Meisterschaft im April in Österreich ausgewählt werden und für den internationalen Wettbewerb, dem GYPT. Schon mal so viel, es sind da Menschen dabei, Schülerinnen und Schüler, die noch keine Medaille um den Hals haben, also es wird noch spannend. Aber ich muss euch noch ein bisschen auf die Folter spannen, weil wir möchten noch jemanden danken. Kommst du bitte nach vorne? Genau, danke, dass ihr schon so viel klatscht. Ich weiß gar nicht, ob ihr es alle wisst, aber es ist ja der 12. GYPT und Michael hat eigentlich das Ganze ins Leben gerufen. Von Anfang an war er dabei und er hört jetzt auf. Es ist sein letzter Bundeswettbewerb und deswegen steht hier so ein großes Danke, Michael. Es möchten ein paar Leute noch was dazu sagen. Ich glaube, Anja, ganz kurz am Anfang.
Danke, Liane. Genau, ich drängel mich einmal kurz vor und ich werde auch gar nichts zum GYPT sagen, weil ich glaube, das machen Sie beide gleich noch. Aber Michael ist auch Mitarbeiter der DPG-Geschäftsstelle und da möchte ich mir das heute
Workshop teilnahmen. Vielleicht, es wissen, glaube ich, nicht alle. Genau. Ihr habt ihn aber, glaube ich, das ganze Wochenende schon gesehen. Das ist Horst. Horst ist seit, ich weiß gar nicht wie vielen Jahren, seit vielen Jahren das Maskottchen des internationalen Teams. Der fährt mit zu den ganzen IYPTs. Genau, er hat einen eigenen Insta-Account inzwischen, darf ich sagen. Das wird von ehemaligen verwaltet und jetzt beim nächsten IYPT halt von dem neuen Team, was wir noch nicht kennen. Genau. Und wir treffen uns Ende März in Ulm zu diesem Auswahlworkshop mit den besten 12 Einzeltamen von euch und werden dort entscheiden, wer Horst dieses Jahr quasi betreuen darf. Und da wir uns in Ulm treffen und die Ulm Mitveranstalterin ist des GYPTs, genau, ist Seniorprofessor Ottmar Marti, der Laudator für...
Danke vielmals. Es ist ja hier eine gute Tradition, die Spannung noch etwas aufrechtzuerhalten. Also Uni Ulm sagt wahrscheinlich nicht allen etwas, aber unsere Studierenden haben in einem deutschlandweiten Ranking gesagt, dass die Uni Ulm aus Sicht der Studierenden die 7. beste Universität in Deutschland sei. Man kann hier Naturwissenschaften, Ingenieurwissenschaften, Mathematik, Wirtschaftswissenschaften und alles, was mit Medizin zu tun hat, studieren. So, das war der Werbeblock. Es gab ja, wenn man die zusammengezählt hat, gab es ja wesentlich über 12 Leute, die eine Bronze, eine Silber- oder eine Goldmedaille bekommen haben. Auch von mir herzlichen Glückwunsch an all die anderen. 12 Personen dürfen mitfahren, das heißt, es werden nicht alle, die eine Medaille bekommen haben, mitfahren. Und es wurde auch schon gesagt, dass es auch Personen gibt, die keine Medaille haben, die mitfahren dürfen und die, um die Spannung noch etwas hochzuhalten. Also Workshop-Teilnehmer, die schon eine Medaille bekommen haben, das ist mit 26,4 Punkten Herr Maxim Rasch. Mit 25,37 Punkten Herr Benedikt Baum. Beide aus Lörrach. Dann mit 25,31 Punkten Herr Rushil Sai Nutalapati, Berlin. Dann mit 24,94 Punkten Herr Vibod Somani. Mit 24,4 Punkten Herr Kurt Stiller. Mit 23,49 Punkten Herr Benjamin Graf. Mit 23,27 Punkten Herr Simon Hermes. Mit 22,54 Punkten Herr Nikita Petrov. Mit 22,16 Punkten Frau Elisa Schöps. Mit 21,66 Punkten Frau Jara Pfeiffer. So. Wenn ihr gezählt habt, dann sind wir jetzt bei 10. Es sind noch 2 Personen. Das eine ist mit 21,67 Punkten Herr Tobias Hossfeld, Dachau. Und die andere Person ist mit 23,87 Punkten Herr Alan Stranjak aus Erlangen.
Nach links, der auch noch von der Seite nach links, schön kompakt zusammen. Okay, alle zu mir schauen, lachen, einmal ruhig. Okay, alle zu mir schauen, lachen, perfekt. Okay, perfekt. Jetzt will auch mal Martin auch noch. Okay. So, alle nochmal zu mir schauen und lachen, perfekt.
Genau. Und das bedeutet jetzt, das ist eine Ehre, die mit noch etwas Aufwand verbunden ist, nämlich ein Auswahlworkshop in Ulm und dann hoffentlich für diejenigen, die das sich besonders stark wünschen, Fahrten zum IYPT oder AYPT nach Wien, also das ist das Austrian Young Physicists Tournament und nach Lund. Also ich wünsche Ihnen alles Gute und viel Erfolg beim Vorbereiten. Macht's gut.
Dankeschön. So, danke. Ihr dürft euch schon mal wieder hinsetzen, aber noch nicht weglaufen. Ich brauche euch noch, aber genau, wir sind fast durch. Medaillenpreise sind alle vergeben, noch ein paar organisatorische Sachen zum Schluss. Die 12 Workshop-Teilnehmenden, für euch ist, wie gesagt, noch nicht ganz Schluss. Wir treffen uns hier im Anschluss direkt an die Zeremonie oben in dem ehemaligen Matchraum E. Dort gibt es für euch auch Essen. Ihr müsst nicht runter in den Keller. Und eure BetreuerInnen oder auch die Projektmentorinnen von euren Versuchen, die können gern mit hochkommen, für die gibt es auch Essen oben. Also direkt im Anschluss hier treffen wir uns oben, Matchraum E bzw. F, in den beiden Räumen. Alle anderen, für euch gibt es unten im Keller gleich Essen. Hinten, hinter diesen Pinnwänden, vielleicht können diejenigen, die hinten sind, die Pinnwände zur Seite schieben, sind eure Teilnahmeurkunden. Also auch für die, die Medaillen bekommen haben, die keine Medaillen bekommen haben. Es gibt für alle Teilnahmeurkunden. Nehmt euch die einfach weg, die sind namentlich sortiert, beziehungsweise nach Team sortiert. Nehmt euch bitte noch ganz viele Plakate fürs nächste Jahr mit, dass wir hoffen, dass noch mehr Leute von euren Schulen kommen. Überredet eure Lehrkräfte und Schüler und Schülerinnen, die ihr kennt. Genau. Eure Bewertung, individuellen Bewertungen findet ihr im CC, im Kontrollcenter, ungefähr ab 13 Uhr. Nagelt uns bitte nicht auf 13 Uhr fest, es könnte auch 14 Uhr werden. Ne? Wir sind mit den 12 Workshop-Teilnehmenden noch beschäftigt. Genau. So. Das war's, ihr steht jetzt schon. Das war der 12. GYPT-Bundeswettbewerb. Vielen Dank, dass ihr da wart. Vielen Dank, dass ihr fair gewesen seid, dass ihr mitgemacht habt, eure Energie und Power. Ich hoffe, ich sehe ganz viele von euch nächstes Jahr auch wieder. Vielen Dank. Tschüss und gute Einreise.